Hello everyone, today we'll see how we can calculate reactive power for a three-phase circuit, for a polyphase circuit and for a single varometer circuit. So first we'll see how we can measure reactive power for a three-phase circuit. So reactive power is given by the expression P is equal to, so reactive power we given is represented by Q. So Q is equal to Vi sin phi. So in load monitoring, the measurement gives the operator or the load dispatcher information concerning the nature of the load. So ratio of reactive and active power is given by tan phi. Tan phi is equal to Q by P, where Q is the reactive power, P is the active power. So there are three kinds of power: active power, which we represent in P, and reactive power, which we represent in Q, and apparent power, it is represented by S. So what is active power? Active power does work and it is in the real axis. And if we take a graph, or if we take a diagram like this, so this is your active power. So this portion is the active power which lies in the real axis. And reactive power does not work and it lies in the imaginary axis of the vector diagram. So this is the reactive power, and it is the it does not work and it is in the imaginary axis, and it is given by Q, and it is nothing but I square X, and this is given by I square R. And apparent power is expressed in volt amps and is a product of RMS voltage and RMS current, and it is represented by S. So S is nothing but I square Z. So this is how we represent three different types of power. So active power, reactive power, apparent power. So active power lies in the real axis, reactive power lies in the imaginary axis, and apparent power, it is nothing but the product of RMS voltage and current. So apparent power is measured in volt amps, and active power is measured in watts, and reactive power is measured in volt amp reactive. So VAR, the unit is VAR, and here the unit is watts, and here the unit is VA. So these are the types of power. So now in today's presentation we'll see how we can calculate reactive power in three different types of circuit. So first we'll take a three-phase circuit. So we can see we have a load, and in three-phase circuit it is a balanced circuit. It is simple to use a single voltmeter to read the reactive power. The current coil is connected to one line. So we can see the current coil is connected to one line. So 2, it is connected to 2, and the voltage coil or the pressure coil is connected between two lines, 1 and 3. So current through current coil is I2, and voltage across the pressure coil is V13. So supply voltage V will be equal to V13 by root 3. So reading of wattmeter is equal to, so reading of wattmeter in three-phase circuit will be equal to V13 I2 cos 90 plus phi. So this cos 90 plus phi is taken from the phasor diagram. So we can see the phasor diagram. So we can see there is a phase angle difference of 90 degree plus phi. So this portion is 90 plus phi. So it is between V13 and V3. So line voltage is represented by VRB. So this is phase voltage VB. So this portion will be 90 plus phi. So between this portion, so we can see we have a 90 degree, more than 90 degree here. So this is more than 90 degree. So based on this, when we write equation for this VRB, VRB is nothing but the line voltage. So P is equal to, from this phasor diagram, it is VRB into VRB into IY cos 90 plus phi. So between this voltage and this current. So 90 plus phi. So again, when we substitute the formula of cos A plus B, it is nothing but cos A cos B minus sin A sin B. So on substitution we get VRB, which is nothing but line voltage, IV into cos 90 cos phi minus sin 90 sin phi. So cos 90 is 0. So this whole thing will become 0. So I get minus VRB IV sin 90 is 1 sin phi. So VRB is the line voltage. So when I convert with the phase, when I replace with the supply voltage, I get minus root 3 VI sin phi. Line voltage and supply line voltage and supply voltage are different. Okay, so line voltage will be equal to root 3 into V, but line current and supply current are same. So I substitute with I. So the phase angle for this will be equal to tan inverse of Q by phi, where Q is the reactive power and P is the active power. So this is how I measure power for a three-phase circuit, and this is how I measure the angle for a three-phase circuit. Okay. So now we'll see how we can measure reactive power for a polyphase varrometer. So for a polyphase varrometer, we can see we have two wattmeters. In three-phase circuits, the phase shifting is necessary for measurement. The reactive power is obtained by phase shifting the transformers. So we can shift the transformers and we can find out the reactive power. The phase shifting is done with two auto transformers connected in open delta configuration. The currents are connected in series with the lines. The potential coils are connected to common terminals of two auto transformer, and phase 1 and phase 3 lines are connected 100% tap on transformer. So the currents are connected in series. So the current coils are connected in series for both the wattmeters. And the potential or the voltage coil, the pressure coils are connected to the common terminals. So transformer will produce 115.4% of line voltage across the total winding. Each wattmeter produces 57.7% tap in transformer T1 and T2, which produces a voltage equal to line voltage by shifting by an angle of 90 degree. So we can see here, so when two wattmeter constitute, you get 115.4% of reactive power, and for 1 wattmeter we get 57.7% of reactive power. So when we put that in the phasor diagram, so this is with 2 wattmeters. So 100% is what we expect. When we use 2 wattmeters, I get 115.4%, and for 1 wattmeter alone I get 57.7%. So for 2 wattmeters it is 11.4, for 1 wattmeter it is 57.7. So I can have the same thing here, 57.7%, actually 100%. But when we use 2 auto transformer, I get 115.4%. So this is how we get the reactive power when we use 2 auto transformers. So this is the phasor diagram for a polyphase parameter. The wattmeter reads the reactive power consumed by the load. The arithmetic sum of 2 wattmeters is equal to the total reactive power supplied to the load. So the arithmetic power of 2 wattmeters will give me the total reactive power. So total reactive power is nothing but the wattmeter readings of both the wattmeter. So now we will see how we can measure the reactive power in a single phase parameter. So in a single phase parameter, the pressure coil has a large inductive reactance and is substituted with series resistance, which is quadrature in nature. So what happens is, in a 3-phase circuit, the line voltage and current has a phase angle of cos 90 plus phi. But here for a single barometer, it lags by an angle of cos 90 minus phi. Again, it is from the phasor diagram. So on substitution, we get cos 90 cos phi plus sin 90 sin phi. So this becomes 0. So it is equal to Vi sin phi. So this is the reactive power for a single phase parameter. And for single phase parameter, the phase diagram will be like this. So we can see the current and the voltage lags by an angle of 90 minus phi. So it is 90 minus phi. So this is how we measure the reactive power for a polyphase parameter, a single phase for a 3-phase circuit, and for a single phase parameter. So the textbooks are A.K. Sahani and Kalsi. Thank you.